All right, it's time for lightning talks. Benjamin, where are you, my dear friend? Okay, I'll do the first two. How's that? Would that be helpful? Okay. So Benjamin is a dear friend of mine from Corelight. I'm not even going to do more than that so that you have more time on stage. Brandon, you're up next. Where the fudge is Brandon? All right, I'll find him. You're up.
So it's a lightning talk, right? So that means I go lightning fast. Boop, boop, boop. Yeah, so do we have the slides? Yes, we have the slides. I have the slides. Yeah, so I want to talk to you about the parser builder that we built for the Zeke project, which is called Spicy. I'm not sure you've heard of it, but I hope you will learn something about Spicy. So the Zeke project is, I don't know if you're familiar, just a brief introduction. So Zeke taps into network traffic and then extracts some interesting information, kind of similar to what Suricata does, and it's used and deployed since a long time, developed in C++ with a core, and it's extensible with its own scripting language or C++, and it's released under permissive license. The architecture of Zeke looks kind of like this. So this is for a protocol analyzer. So we get some packets from the network. Then we have some magic event engine, which does the packet parsing, for example, TCP reassembling. Then it feeds that data into analyzer components, which could be either bundled with Zeke or installed as an external component. That analyzer then extracts other data from that. And for example, you could have an HTTP analyzer that extracts a post payload, which is a file, right? And that gets fed back into the event engine and fed to another analyzer again and again. Or an analyzer could also raise events, which are then handled by scripts. So scripts, they can consume events and also raise other events. And eventually, at some point, we create some log that some analyst looks at. So how do we add new analyzers to Zeke? So historically, you needed to write C++ code, and C++ has a kind of like a significant barrier of entry, and the code can be pretty, even though you have like high-level abstractions in C++, there's like still a mixture of your interesting protocol implementation and just C++ housekeeping. And it's also not a safe language. So I saw some talks on fuzzing, on CodeQL, and like even for sure I have bad days where I get like integer promotion wrong, right? So can be tricky. So the idea was to create a high-level language for parsing, which allows you to, at the same time, be descriptive, but also go down to low-level programming without writing C++, a safe environment. And it should be efficient enough so we can use it in Zeke to parse thousands of connections at the same time without overflowing memory or having too much overhead. And it should be possible to somehow integrate that transparently and in a nice way into Zeke. So a colleague of mine, Robin, started a project, it was a research prototype almost 10 years ago. It was called Hilti, maybe you've heard of that. And that we now re-implemented and now use actively in the Zeke ecosystem to write packet analyzers. So that's the low-level stuff where you could have your, you could analyze TCP in Spicy if you wanted to, or we have protocol analyzers which analyze more high-level things, or file analyzers. And we are in the Zeke GitHub org, and we're also on the Zeke Slack. So now let's go into some code. So TFTP, very simple protocol. I mean, it's in the name of the protocol. So you see there's like two major messages, like read or write. So a client could say like, hey, give me this file, and then the server answers back with data packets and acknowledgements all over UDP, or the client could upload some file by issuing a write request, and then pass the data to the server. So let's implement a simple parser for that, or some outline at least, right? So on the top you see how the protocol is specified. So we have some opcode, 2 bytes, we have some file name, which is some range of bytes terminated by a 0 byte, and some mode, which is another string terminated by a 0 byte. So how would you write that in Spicy? You would have a unit, which pretty closely, I hope you can see that, follows that specification. So we have some op, which is an uint16, so that's our 2 bytes. And then we have some read requests. So we don't have to implement everything here, but we can delegate to a different parser, which you see down there. So there we extract a file name, which is just a range of bytes until we hit some 0 byte, which we consume from the input but throw away, and a mode, right? Similar pattern, and we can integrate that in there. And then you also see this done hook, so there's a mechanism where you can plug into the parsing progress. What we do here is that we just output the default string representation of that unit once it's filled, right? You can customize the printing. Let's go a little further, right? So let's put some semantic meaning on that. So on the very bottom, you see the opcodes, right? A read request with that byte pattern, a write request, that byte pattern. And we can, in the packet on the top, we can still extract that uint16, but then invoke some function on the field we just passed. So that's what $$ stands for, and we construct an enum value now here. And then, since that we don't have a naked int anymore, we can switch it over it in a meaningful way that kind of you can also maintain instead of just writing, right? And here we branch for read request, we branch into a request parser at the bottom, which takes a parameter. So this request is a read request, okay? Or in the other case, is read false, it's a write request, right? So, and this parameter is implicitly in, and we also have in-out parameters. And you could imagine how you kind of build that out, right? Is everybody still following, or am I going too lightning? Good. So now I'm giving you some basically everything other interesting stuff that you should see. So another use case you typically see when you pass traffic from the network is that you don't capture something. You have like you didn't capture the packet and you just have a gap, or you have a parse error where your parser doesn't really match what it sees. And so since we formulate our grammars on a high level, we can actually have automatic support for that. So like you see in unit foo at the top, right? You see a field x. So what the syntax here is, this is a list of x's, and we don't really know how many. We just do look-ahead parsing and try to extract as many as possible. But this x is annotated with the synchronize attribute, which means that Spicy will, in that top x unit, it sees that this unit always starts with a certain byte pattern. So we can actually resynchronize on that byte pattern again and pick up parsing automatically, right? We can also do that in a single unit. So this bar unit on the bottom, if you imagine we would fail to parse, or we would have a gap at field A, we would then skip to field C and try to find that synchronization pattern, whatever that is. That could be some literal, it could be a number of constructs. We also have some support for more low-level backtracking if you need that. For example, to try out what something conforms to. Going more into the conversion thing, I think this is like one of my favorite features, actually. Users don't really like it so much, I'm not sure. So this is a very naive CSV parser, right? CSV parsing is kind of hard, but this fits on a slide. So CSV is just it's a list of rows. We don't know how many. And a row is a list of columns. And the way this row field is constructed is here we extract bytes until we see a new line. So that's a line. And once we have extracted a line, we invoke a bytes member function, which splits that bytes whenever it sees a comma, right? And the wrong thing here is that if you have quotes, you kind of need to be careful, but you could invoke your own function here. That is more smart. So then our row doesn't contain a bytes anymore, but it contains a list of bytes, right? Comma separated. So when we are done parsing that row field, we could also just extract that data out of there. So we could say, when we are done parsing a row, just give me the list of calls inside that thing and throw away that row. And then we can define a hook somewhere outside also, which just prints that out. And at the bottom, you see how that looks in practice. So I printf something in a program Spicy driver. So this is a thing that can consume raw bytes from the input. It can do jitting and hooking everything up, and it prints out the representation. So this is real code, actually. There's nothing missing here. So how do you extend your Spicy grammars? So let's say you have like a very important cryptographic algorithm that you need to bind in. For example, this encryption algorithm. We can then define in the middle a module which defines a function which is actually implemented as C++ code somewhere else, right? So we just declare a ROT13 function in Spicy, which maps to my library ROT13, and can use that at the bottom. So this is Spicy code that then calls into compiled C++ code and outputs something again. At the bottom, I show you something different. So this is our spicy C, which is our compiler. And we JIT the spicy files and the C++ file together and just run this code at global scope on registration of that module. So the general pipeline kind of looks like this. With spicy driver, we get some kind of grammar. We JIT that, and that means that we build some AST, can do optimizations and transformations on that AST. We emit C++ that you didn't see. And then we invoke a compiler and a linker to create some HLTO file that then spicy driver, in this case, would link in dynamically or statically, however you want, and hook up the parsing to standard input, and also bind some runtime library, which has other tooling that we need, and for the printing, for example, right? That comes from the runtime library. The code that we generate looks, oh, I'm running out of time. The code looks, okay, my 10 minutes are over. So you see like an example unit on the top. So I just emit like the C++ for you in an abbreviated way. You see like we just emit for type X, we emit some struct type that does some C++ derivations and gives you different parser functions. In this case, it takes like a reference to a parsed unit that we modify, the data stream, and some limited view into that, and returns a new view. And that's how you can check how much you consumed, and you also see the data in there. We haven't parsed it potentially yet, so they are both optional. And this parsed unit can be reflected on, and we did some prototype on that with Wireshark. So this is taking our TFTP analyzer and just in a generic way hooking that in. So this is automatically generated code in Wireshark that you see here. Okay, so features I didn't touch on. There's other interesting stuff, and you should ask me about it. How do we use that in Zeke? So since Spicy knows nothing about Zeke, we have a glue layer in the middle which adapts types and matches up Spicy hooks with Zeke events. And we have a DSL for that. So here we define protocol analyzer, which analyzes TCP traffic and maps to some Spicy type. And here's some static port configured. And then we can do some mapping down here. So this is basically a Spicy side hook on the left-hand side. Right-hand side, it's a Zeke event, and parsers typically write some spicy grammar and some EVT file, starting from a template, and then they implement this business stuff in Zeke script. We also have a stand analyzer, since we just showed that, so this is just the statistics. How much do you need to make a meaningful stand analyzer? So you have 160 lines of grammar, 70 lines of glue, then you have some stuff to do dynamic protocol detection, 20 lines, and then you do the really interesting stuff, 270 lines of Zeke code, right? That would look kind of like this, right? So you see, like we have bit fields, all that stuff. So we use Spicy successfully in Zeke, and we are in the process, I think, of moving the bundled Zeke parsers to Spicy, which is a long process. And if you're a Zeke user, please consider starting from the Spicy Zeke AG template. And I would be talking to this community, I would be curious whether it wouldn't make sense to share grammars across communities so we don't have to re-implement all of it and shake out false positives, endpoints that don't conform to the spec, all that stuff, right? So that would be kind of great. If somebody wants to talk to me about that, please come up. Done, 12 minutes. Sorry. Questions, right?
So about the until, do you have a limit, or if I put 4 gigabytes without end of line or whatever, what's happening?
Yes. I mean, maybe you want that, right? We don't really know. So what you can do is you can put requires clauses. So we have like an attribute that where you can put requirements. So what you should probably do is that you put some sane requirements on your fields. For example, if you have like a size and then some user sends you some UN64 max, you trigger a parse error in that case and try again. Yeah. But that's always tricky because you don't really know what kind of crazy stuff users are sending you. Right? So there's some trade-off, and that's stuff that each project needs to figure out, right? So you implement something to spec, we implement something to spec, then we run it on real traffic and make it looser and looser, and that's the bulk of the work, I would say. Yeah.
Thank you.
can come talk to me later, all right? Thank you.